Speaker officer.
Hello, am I audible?
Yes,
Yes.
Nimish, you are audible.
Yes, sir. Yes.
Okay. I'm not able to switch on the camera. Perhaps I joined from a different account. Is it the reason?
No, we
It is
have
not
given
the-
you the permission, audio, video, both. Maybe just
Okay.
log out once and try.
Okay. Okay.
The student mirror. Answer X is asking the delegate. Will she permanent citizen?
Yes, Nimish, now you are able to switch on the camera.
Hello.
Yes, Nimish.
Yeah, I hope I'm audible and visible both, right?
Yes, yes.
Okay.
You're
Thank you.
audible.
Sorry for the glitch.
Okay.
Yeah.
So
No problem.
we'll start with the introduction of the
Yes.
speaker. So good morning, everyone. Dr. Nimish Pankhedkar. He has completed his PhD and postdoc from IIT Bombay, and he has worked across the chemical industry at various positions. He worked as a process design engineer in Technoforce Solutions, lead chemical consultant in 280 carbon systems, and AIML specialist in Grace Davison Chemicals. So he has an extensive experience in chemical industries as well as implementation of AIML in the chemical sector. So today, Dr. Nimish is going to give a lecture on predictive analytics in the chemical industry operations. So over to you, sir. You can start the presentation.
Thank you, sir. First of all, thank you all for inviting me to this session, and I congratulate Dr. Neeta ma'am and entire team of TSEC for arranging this FDP. Because it is a very crucial topic, and while we are transitioning from traditional chemical engineering area into AIML, it is essential for us to know what is emerging and what is required in the industry. At the same time, keeping a track of what we have learned over the years as a domain knowledge. So this is really a good opportunity for all of us to listen to all the speakers. And again, I thank and congratulate TSEC team for inviting a plethora of speakers that covers almost that spans entire chemical engineering sectors, right from the conceptualization up to the operations, maintenance, and so. So with that, I'll just share my screen. Let me know if that is visible to you all. All
Yes,
right.
Nimish, it is visible.
All right. Thank you. So the topic predictive analytics in chemical industry operations are very, very crucial and very near to my heart, because I'll just quickly share some brief of how I came into this. So I started my PhD in hardcore chemical engineering area in CO2 capture, utilization, valorization and storage. But while doing that, I came to a certain point where I realized that, traditional methods for optimizations or control needs a revamp or needs a boost. So with that idea, with that notion, I entered into this AIML area, as it was a booming one. And then I tried to integrate the domain knowledge along with AIML, and hence I transitioned from a hardcore chemical or process engineer into applications into process engineering. And when we talk about the applications into process engineering, the operations become very, very crucial ones, because this is the area where we have a lot of data. Because since the industrial revolution, we have been using sensors, we have been using data collecting software, SCADA, DCS since a long time. So we have a lot of data. What we need, or what needs to be improved, is the transition of data into useful insights. So with that, I'll just pose a question to you all. So let us say that we are in a chemical plant. I hope most of us are chemical engineers over here. So I'll be using the narrative of plant again and again. Yeah, it's nice to see the thumbs up here. So let us say that we are in a chemical plant, and you all are plant managers over here now. So in this scenario, you come to the plant one fine morning and you look at all the parameters on your DCS screen, and you feel, okay, all good, all looks normal. So what you do is you instruct your field operator to take the sample of your product and check its purity, because product purity is something that governs your costs directly, the operations as well as the selling costs. That is why you take the sample at frequent intervals, or once or twice in a shift maybe, and you instruct your field operator, okay, go collect the sample, send it to the lab as per the routine procedure, and you're relaxing in your AC cabin. After a while, let's say 5 hours later, what happens is the field operator comes running with the lab report, and he tells you, sir, the product purity is less than 98%, and we have produced a off-spec material. The 8-hour shift, and the result comes in, and it tells you that all the material that you produced in the previous shift is less than the 98% purity, and it's completely off-spec. So as a plant manager, what do you do in such a situation? Maybe I'll just, ma'am, if we can open this for participants to answer and participate. Any thoughts, any comments? What would you do in such situation as a plant manager?
Recycle operation.
That's right. So you do a reprocessing, probably, right? So you take this off spec, you store it at separate location, you again feed it back. So that again comes up with a huge operating costs, right? But while doing recycle, you need to do a compression process, and then you start a recycle maybe after a certain time, and then you get to know that, oh, my compressor has tripped because of higher load. Now what do you do? So of course this could be a hypothetical case, but anyone is trying to add in here?
Yeah, check the operating data. Why the product is off spec?
Correct.
Is there any
Yes,
change in
yes.
field condition, composition change, which is reflected
Yes.
into off spec?
Exactly, sir. So
Or
basically,
check the hydraulics of the column.
exactly. So what we are trying to do here is, retrospect, go back into the data and check what went wrong. But it will not avoid the harm or the bad that has already done in this particular shift. So as a plant manager, we can certainly think on this. What to do now is, you already answered to that, all of you. Then can we avoid this situation? because what we do now is retrospecting or doing a diagnostics of the situation. But what we could have done is definitely, if we could have got a insights what is going to happen in next 8 hours or in next 2 hours, that would have helped us in two ways. Either take a proactive action instead of corrective action, right? Recycling the off spec is definitely a right corrective action, but instead of a corrective action after the problem is happened on the site, can we do a proactive action and avoid the problem altogether? This is something which we'll be discussing throughout this session today. And so that is why instead of reaction to a problem, we try to do a prediction of the problem beforehand. And that is how the analytics or predictive analytics has become a foundation of AI driven ecosystem in chemical plant operations. So instead of a corrective action, you go for a prediction and try to avoid the incidents altogether. And so basically we use the historical and the real time data, as sir rightly said, to gain insights into the future. So this was just a small scenario that I tried to pose, because when it comes to chemical engineering operations, it is important for us to have a feel where this theoretical concept that we have been learning throughout our education or throughout our experience, how that could be translated into the real-time applications. So with this, I'll just brief you what I have in my mind for today's session. I have a session, this session and second session in the evening. So my idea is to discuss the real-time case studies that I have been doing in industries in the second session. So I'll begin with the introduction, the motivation, and give you a feel why predictive analytics and taking a proactive action rather than reactive action is very much essential to improve the quality, to improve the reliability, and to improve the sustainability of chemical plants. Followed by, we'll discuss some basic concepts of predictive analytics. What are the different layers of analysis? We'll delve into the application areas and typical use case buckets for predictive analytics in chemical industries. I'll walk you through the different data sources that come up in the chemical plant, and what are the challenges, how to deal with them, why are they important. We'll discuss some of the modeling approaches and why the domain knowledge is supreme. Although we talk about AI/ML, I'll share my experiences maybe in the next session, wherein some projects done without the domain knowledge were difficult to implement, although they look lucrative on paper. But when the domain knowledge kicked in, the projects were a hit. So I'll discuss that at length with the case studies. We'll begin with the soft sensor, a very popular application, followed by the optimization and control case study. I'll discuss some framework I have developed as a part of my postdoctoral work, wherein we integrate the process control, soft sensing, inferential control, and how it could be used, and some of challenges and best practices that I've learned so far in the industry, and some insights that I've gained through my seniors and my experiences. So I've tried to keep this session more of a qualitative one, because forgive me, but due to the confidentiality, I may not be able to discuss or answer the questions in detail when it comes to data. But I've tried to mask all these details and try to present the data so that the participants get a feel how the data looks like, how the applications look like when it comes to the actual site implementation. And yeah, I've tried to keep it brief, because I think there are some students also participating. So I've tried to avoid the jargons and try to keep the presentation as qualitative as possible. So with this motive, I'll take a pause and take you back to the industrial evolution. So the industrial evolution, when we talk about industry 4.0, which is a very buzzing word at this moment, perhaps we are going forward for industry 5.0 and looking forward towards the industry 6.0. But let's take a leap back and look at what these industry 1, 2, 3, 4 versions actually meant. So when we talk about industry 1.0, it largely refers to the starting of the industrial revolution era, wherein the steam engine was invented, and the mechanization was the prime parameter governing the entire industries. And when it came to decision making, because industrial is all about the decision making, the decision making were primarily based on the heuristics or on the domain experience only. Coming forward to industry 2.0, when the assembly line was introduced and the production at scale became feasible, became realizable, that marked the use of electrical machines rather than mechanical equipments. Coming forward towards industry 3.0, that is where the computization power improved and the automation boomed really. The electronics components came into the picture, and we just don't rely on mechanical systems or electrical systems, but we also augmented the software systems into our industries, and that really boosted the economy and the scale. Now coming forward to the industry 4.0, it really means that it's not just mechanical, it's not just electrical, it's not just software based, but there is a cyber physical ecosystem wherein the IoT, IIoT come together, and there is an ability of equipments to communicate with each other without any human intervention. So that is the beauty of industry 4.0. And so when I talk about the schema of decision making, initially it depended mostly on the heuristics or the domain experience. Coming towards the second era, the time frame might not map exactly, but this is just an idea of how the process control decision making, particularly in chemical and allied industry, evolved along the years. When the controllers like PID came up and we had simple if-else kind of logics, the decisions were deterministic and were taken at the plant level, directly at the equipment level. Then came the software evolution, and we went into MPC, advanced process control optimization domain, and there the decisions were taken by the loop directly rather than giving the data or needing any human intervention. But now when we have a lot of data and we have a very higher computing power, the AI ML or the agentic AI has taken a driver's seat, and the decisions are made not just at the plant level, not just at the instrument level. It is considering a different section. It is considering the energy, it is considering the operations, it is considering maintenance, and different areas or their data insights from different domain has come together, and it has become possible to take a decision keeping in mind a holistic picture or a larger picture for the entire industry. So I'll move forward with the crux that industry 4.0 is not just about automation. Automation is a thing of past, but now we are into anticipation, and when anticipation is important, we try to avoid incidences. We try to improve the plant profile before any incidents occurs, and that is why it is all about anticipation. So if we look at, coming back to the chemical plant, if we look at a typical life cycle of a chemical plant, it starts from the conceptualization, the feasibility studies, then come the basic engineering package, the detailed engineering, construction, commissioning, and operations, and finally it goes off with the decommissioning over its entire life cycle. So believe me, each and every stage of this life cycle has a vast applications of AI ML coming into the actual realization, right from using different models to to generate better materials, better polymers, etc. Into the conceptualization, using a lot of automated or agentic frameworks into designing of the process flow sheets, process diagrams. Then coming into the construction, again a widely explored field. So every stage is largely impacted or benefited, I would say, by the revolution of AI, and that is why I'll be focusing on the fifth stage, that is the operation and maintenance, because we have a lot of data into this bucket since a lot of years, and the maximum value addition done so far is coming from this bucket, because as it says, it's day-to-day operation, so it hampers day-to-day, and a lot of research focus is going into this bucket as well. So coming with this motivation and introduction, coming to the actual concept, I'll first start with the different layers in the analytics. So I'll take again the example of the initial problem, or the initial the initial study that we discussed, where the product purity was off spec. So what first level of analysis is the descriptive ones. So where we look into the data, or where we look into the details and come up with an answer to the question, what has happened. So when the lab report came, when the data from the lab came, we understood that, okay, the product purity is off spec. So that is basically the incidents in the past has happened, and now you are looking at the past or present perhaps, and then you are looking at the data and giving a verdict. Next comes the diagnostics. So as sir rightly suggested, we'll look into the data, we'll do a root cause analysis and try to find what was the issue leading to the generation of off-spec material. So we go and look into the data of what was the issue. So maybe the answer could be that, okay, the upstream composition has changed, the feed composition has changed, for example. Now what? So these are the these two buckets are where we take reactive or corrective action. But coming to the predictive analytics, we come up with an answer to the question, what is likely to happen. So we will be able to take an action well within time, and that goes to the next level, that is the prescriptive. So the predictive analytics is all about finding the answer to the question, what is likely to happen, and the answer to how to avoid the incidents if it is going to happen. That comes up into the topmost layer of the prescriptive analytics. So for example, we know that the upstream composition is drifting over the next 2 hours, then probably the operator may take a decision to increase the recycle ratio so as to maintain the product purity. So these are the different layers in analytics that most of you would be familiar with. So any questions so far? All right, that's good. So coming towards the core concept of predictive analytics. Predictive analytics, as I mentioned, is gaining insights into future by using historical or the present data. So it is essentially a simple dynamic mapping problem. So if you look at this equation, let's say that you want to predict the parameter y at a certain time delta t. So what you do is you try to map it with the available state variables, available process variables at time t, also at a time before t, along with the manipulated variables that you can control. There could be some variables that you can just observe or just look at it, but there could not be any control handle over that. So those, along with the ones which have an explicit control handle, and the process disturbances that you don't have control on. So you try to map in the time domain the y variable along with this variables, and this is what is basically the basis of predictive analytics. So now natural question that I as a chemical engineer ask is, okay, this is what you're telling me, but we have been doing this over the years. So we have physics based equations wherein we are able to estimate what will happen at t plus 30 minutes, for example. So let's say that there is an equation dy by dt as a function of g x u p, and you can easily calculate what is the value of y at certain time t plus delta t. However, when it comes to solving and the computational power, the physics based or the first principles models largely depend upon the computational power and solving a lot of differential equations. So we have several methods for solving the ODEs, PDs, etc. So that are computationally highly intensive. So let me take up an example of estimating the reactor temperature after 30 minutes. So there are two options to do that. One is you can easily write a material and energy balance and come up with this kind of equation. There could be certain more equations which you need to solve simultaneously. You write a Python code or a MATLAB code, or if it is a complex problem, you go to a CFD, you do the meshing, then you run the solver, and maybe after 1 day or 2 days, you get the result. So in the research case, it is quite good because you need a very high accuracy. But when it comes to industrial, you need to take decisions very quickly. So in that case, developing a dynamic map of what has happened in the historical data, can we predict the future based on the historical data only, becomes very crucial and becomes very important. So intuitively, if there are these two equations, if I would have further simplified this, everyone would have said, okay, let us use the second equation because it is easier to solve. It may not be interpretable. I'll come to this interpretability and domain reasoning maybe later, but just passing a reference to this at this point is interpretability in prediction is very much important, because some things might look mathematically correct, but they might not have a physical significance in the chemical industry. And that is where the importance of domain knowledge comes in, because you should know that something is mathematically correct, okay, but it cannot happen it cannot happen physically. This distinction may not be available with a person who is not well versed with the domain. So if I have to broadly differentiate between the first principles and the methodologies used in the predictive analytics, predictive analytics has been hijacked by the data science. Although you can do a prediction based on first principles also, but it is nowadays mostly coupled with the data science notions only. So the model form is in first principle, you can have a known equations and you can have physically meaningful equations. But in case of data-based models, you might have to learn from the data, look at the historical pattern, look at the trend, and then predict what might happen in the future. The parameters are quite implicit in case of the predictive analytics. You might not have a separate variable for that, but it is implicitly included when you look back into the history. Accuracy, it's fair enough that the accuracy is limited by assumptions in the first principles, and it is governed by the data in when it comes to a data driven model. Adaptability of first principle is again low in industrial operations, because the time taken to solve is quite crucial over in the operations. So that is why the adaptability of data-driven models is quite higher in the industrial setting. So with this, I come to the application areas, or broader or upper level buckets wherein we can implement this predictive analytics in an industrial operation and maintenance region strictly, because if I start listing everything, it will be a big review paper. So I've just segregated the different use cases into 4 buckets. One or the foremost and the primitive ones is the process and quality bucket. So the popular soft sensors are all into this process and quality bucket, wherein you try to predict the future quality parameter. So for example, in our initial case, if I had a model that would have told me, okay, the product purity in next 2 hours will be off spec, you could have immediately taken an action on that. right? So this is where the process and quality is very crucial and highly impacting in terms of costing, because any reactive action you take, maybe let that be recycling the product, or even if it is a tripping of some equipment leading to a plant shutdown, it all incurs a huge amount of cost, a huge amount of penalty on the dollar values. So it is quite popular and widely used application of predictive analytics is in predicting the process states and the product quality parameters. Next is the operational efficiency and optimizations. Sometimes you might feel that, okay, the operation is all good, all normal, but the day-to-day plant operator might not realize that there is a scope in further improving this efficiency, or in further optimizing the process parameters. So I'll discuss a case study where we tried to optimize a highly expensive raw material, wherein the plant operators had only insights to, let's say, the 8 hours. They are all occupied with, lots of day-to-day activities, and they might not have that hunch on what is going wrong. For them, only the KPI is the parameter. So let's say KPI is intact, all good. But sometimes what happens is, in order to maintain that KPI, you sometimes use lot of raw material. So you might have a product purity of 99%, but your yield might be dropping at that point, because you are using excess raw materials. In that case, I'm just stating an example. I'll again circle back to this when I discuss the exact case study that we did around this bucket of operational efficiency and optimization. So just to close this as of now, certain parameters like energy, yield, throughput, losses, etc. could be further optimized, although the process quality is in line. So you try to predict the consumption and then prescribe parameters to optimize. So it is not just predictive analytics. There is a prescription layer sitting on top of the predictive analytics that is giving us the benefit in operational efficiency. Next is again a very important safety bucket: safety, compliance, and stability, also sustainability. So the predictions of emission, or whether the process is embarking on breaching a safety limit, this kind of predictive analytics is highly important. Again, to look at the constraint violations, look at the events that are not supposed to happen, is again important. For example, this I've cited an example of prediction of reactor runaway reaction, or if there is a spike in emission. Particularly, this becomes crucial in terms of plant startup or shutdown, wherein a lot of activities and a lot of dynamics is happening, even if it is a continuous plant. And last, and again one of the most important, is the asset health and reliability. So again, in as far as industrial applications is concerned, as per my knowledge, again this asset health and reliability is has given a lot of dollar value, has given a lot of value addition in overall plant efficiencies. So instead of doing a reactive maintenance. So when I talk about reactive maintenance, let us say that there is some problem going on with the plant. You go there, you try to rectify the problem, and you understand, okay, you need to take a shutdown. You take a shutdown, your operating hours are lost. You do a maintenance, and then you again come back and start the process. These shutdowns, which are unplanned shutdown, are again a huge penalty to the chemical industries. So a lot of efforts are taken trying to minimize this unplanned shutdown. So for example, let me take a heat exchanger. A heat exchanger having a heavy fluids, having a lot of solids or higher TDS, you might expect it to foul quite early, right? So how early? Instead of the exchanger not performing well, and then there is no heat transfer happening, there is no cooling or heating taking place, instead of taking an action at that point, there are a lot of forecasting models that forecast the run length of the equipment, and based on that you can schedule your planned shutdowns. You can schedule your maintenance. Let's say you have standby pumps, 2 pumps. You get to know that, okay, this pump is going to fail in next hour or maybe next day. So today only you take an action. Instead of diagnosis, you do a prognosis. Today only you take an action that you cut down that pump, you use a standby pump and shift to that pump. So these kinds of actions that are generated based on data driven insights are all very crucial for the asset health and monitoring reliability. Just a quick reference to a study that was done by an industry recently. So what we try to do over there is we try to analyze the work orders. So work order is basically a document that is generated when you need to do some mechanical operation, or you need to do some repair work on any of the equipment. So you need to document it, what was the work done, and then there are priority of work orders. So there are typically P1, P2, P3, P4. So based on different nomenclatures, P1 is usually the urgent that is impacting either your safety or your production. So those kinds of repair has to be attended very quickly, irrespective of whatever cost is required to conduct that repairs. So P1 work orders, P2 work orders, P3 work orders, P4 work orders. P4 are usually planned work orders or planned repair work. So after adding some sensors wherein we can measure the vibrations, particularly for rotary equipments. So what the models try to do is models try to analyze the pattern of a normal operating regime and try to compare the current pattern with them. If there is any shift in the vibration pattern or temperature profile, pressure profile, for example, in the distillation column, you try to match the typical pressure or temperature profile with the current one. And if you see there is deviation, you might come up to a conclusion that there could be some problem. You might need to take a shutdown, clean, or whatever work you need to do. So after implementing the predictive maintenance models, what we observed is a 35% drop in the P1 work orders. So whatever work orders were scheduled as urgent, the number reduced and the number of P4 increased slightly. So instead of taking a urgent shutdown or urgent repair work, you try to predict it earlier, schedule it properly so that your operations and safety is not hampered. So I just tried to give you a gist about different buckets where the predictive analytics could be implemented, or rather is implemented in chemical industry. Because I remember yesterday Dr. Neeta ma'am mentioned that AI ML is no more a buzzword. That is absolutely right. There is a lot of actual work going on, and not just work, but a lot of value is being realized by implementing these models in the industry, and not just at pilot level but at a larger scale also. So I'll just give an example. So whatever I discussed about soft sensors, I'll just try to walk you through. Instead of discussing the case study in the evening session, we'll at that time we'll go into more details, but I'll just give you a gist what exactly soft sensors are. Most of you would be familiar, but for those who are new to this area, so let us say that presently what is happening, I have a feed which is going to the reactor, and after the reactor the product goes to a downstream operations, most likely the separation operations, the distillation operations, and the product is taken. The product is sent to the lab. The sample is sent to the lab for analysis, and after a delay of 4 to 6 hours, depending on how labor intensive the quality tests are, you get to know the result. After the result has come back, the production is already gone. After the result has come back, then the operator takes the decision based on his experience. Okay, I need to increase the temperature, or I need to increase the feed. I need to do some corrective actions. But again, in that case, you are losing that crucial period of 4 to 6 hours of quality. That is why what is the proposed strategy of soft sensor is that you develop a model that will predict the purity. So whatever is happening in lab, you try to mimic the same using the historical and current data, and you develop a soft sensor. So it's basically whatever parameters you cannot measure physically. For example, composition, we do have composition analyzers, but let's say they're very costly, or if particular component doesn't have an analyzer. and you are not able to have a real-time reading for that analyzer that is forcing you to send the sample to the lab, what you can do is use the data that is available, use the data of all the physical sensors that you have on plant, maybe flow meters, thermocouples, pressure sensors, etc., and you try to map it with your quality parameter. So this is a simple regression problem wherein you have y equal to f of x1, x2, x3, x4, etc. And once you predict y in a fair bit of accuracy, you can then use that information. The operator will get, there is no time delay over here. The operator will instantly get to know, okay, because of some changes in the feed or upstream composition, my product quality is likely to drift. So what you do is the operator, based on his experience, can immediately take the corrective action. Let's say he wants to increase the feed or decrease the temperature, whatever. So this is a typical block diagram of a soft sensor. Now what? Now let us say that the operator is quite new. My operator has changed. The operator doesn't have experience. So even though you tell him that, okay, my product quality is so and so, or it will change to so and so in next 2 hours, the operator will not be able to take a right action. So what you do is, instead of just predictive analysis, you try to put up a prescriptive layer on top of that. And now you say that, okay, my I'm taking the readings of my feed, I'm taking readings of my temperature, pressure, different variables for which I have sensor data. I'm developing my ML model. I am predicting my key performance indicator, and then I will run an optimizer using that model, and the optimizer will tell me my recommended feed. So this is the AI driven optimizer and control strategy, wherein the operator will get an insight also, not just what is my KPI, but what should I do to maintain my KPI in a good limit. That is what the ML models can do wonders, and it can help the operators take the decisions. So as Professor Goody also mentioned yesterday, it is not just about artificial intelligence, but it is mostly on the augmented intelligence that we are talking, wherein the domain knowledge comes hand in hand with the data driven insights. So I hope this part is clear. I'll just pause a bit to take any questions on soft sensors particularly. Yes, I can see Aditya raising hand. There is one more, I guess.
Hello.
Yes, yes.
Hello. Yes, am I audible?
Yes, you are.
Yeah, I had a question, just a small question between this advanced strategy and the previous slide. So you said that whatever changes will take place, like based on optimization, like this proposed strategy, the soft sensor one, and the lower the advanced strategy. So in the first case, the regression analysis that you will do to measure how much your purity is deviating from your calibration. Basically, you will do some of residuals and all that. And then you will identify, okay. So that data will then be passed on to the operator, who is then expected to make changes in the operating conditions.
That's right. So just to clarify and just to add one more point over here is the data that you are taking from the plant. You'll try to develop a simple regression model which will predict your KPI in that case, and the operator will directly get the value for that KPI. So whatever the lab will tell him after 4 to 6 hours, it will get it either at the real time or even in future. I mean, even the future readings could be available to him for a certain horizon window.
Okay, and you're telling that in the third case, that is the advanced strategy, this regression will be fed to an AI model, and the AI model will make the changes automatically within the system, within the operating system.
Correct. So it depends now. So I've just in this schematic, as you rightly said, if you are confident enough that your AI driven output is absolutely good, it has all the constraints, it is not violating any safety limits, you can directly instruct or you can directly link this. Instead of operator, I can have a APC block over here, and that advanced process control block will directly take a corrective action over here. Right.
Gotcha.
So instead of operator thinking ki, okay, let's say my KPI has now increased, what the product purity is now decreased, you got to know from the regression that okay, my product purity is reduced. What should I do? The operator thinks, okay, shall I increase the reflux ratio, or shall I increase the reboiler ratio? That thinking you needs to do. So instead of that, what you can control the flux ratio, you can control the reboiler ratio, you can control, let's say, some condenser temperature or some cooling you can improve. So you know what you can control. So you develop an optimization, you tell the optimizer, okay, these are my constraints, these are my possible control handles. You try to vary reflux ratio, you try to vary the reboiler ratio, you try to vary the condenser temperature, and along with that you tell me what should be the combination of my reboiler ratio, reflux ratio, condenser temperature to maintain my product purity above 99%. So that value directly the optimizer is capable, or you have to make it capable to give you that value, and you can link it directly to the controllers.
So there will be an equation that is developed and for interaction between all parameters, and then that will
Correct.
be optimized over several runs.
Correct.
And the
correct,
final
correct.
equation that you get with the most, that gives you the optimized conditions, will be fed to this APC model that you are suggesting
Right.
instead of the operator.
Right,
Okay.
right. So basically, what you get is the set of best operating parameters is your output that you can get from the optimizer.
Oh,
So whatever
thank
activity
you.
the operator does manually, you can automate that with the help of optimizer. Because every time in the real time, if you are sitting on a panel, DCS panel, you will not open Aspen, and we cannot try to do a simulation. Okay, what is happening, or what will happen if I increase my feed temperature, what will happen if I increase my reboiler ratio, reflux ratio. You don't have time over there to do the simulations and then come back and tell, okay, I'll increase feed. Till then everything would have gone. So that is why you need to have a model that is capable of prediction. Now you know for these parameters, this is my y. Now what is the best parameters to get the y above 99%? That is what this optimizer block is doing. So I'll just try to recap this whole thing. So the first ML model will just tell you for x1, x2, x3 what will be my y, and the optimizer model will tell you for my particular y requirement what should be my x1, x2, x3. So it's basically inverting the prediction model and trying to find the best optimum. I hope I've answered your question.
Yeah. Thank you.
I think there was
I
one
want
more
to ask one question.
hand.
Yeah.
Yes.
You discussed the distillation column of spec product.
Mhm.
So what are the soft sensor this AI modeling? And suppose you say that with density or some property will estimate soft sensor, then how do you validate the actual? Because the incoming fluids, they might be non-ideal or variable composition. So how do you mitigate that risk? Those are two
Correct.
questions. What is a soft sensor, and second thing, how do we validate that?
Right. So since you took an example of distillation column, so what mostly is developed is the composition analyzers are the soft sensors. So in my initial example of of the DMA distillation, or let me take an example of ethanol water distillation column, it is crucial for me to know what is the top purity at every point of time. So you might have to correlate the temperature profiles, whatever you have. You might need to correlate the upstream compositions if you have the analyzers for them. If not, you have to use the historical data or the data in parts. So that is the challenge. I'll be coming to that in the next session. Like, what are the challenges you face? You might not have data at every minute for developing a model. You might have a data at every 6 hours, for example, for my feed composition. So to answer your first question, the soft sensors to predict the top and bottom purities or entire composition profile are widely used when it comes to distillation column. And secondly, as you asked, what could be done to validate the model outcome. So there are two things. You have a historical data, you split that into some parts, you try to check whether your model is having fair bit of accuracy, having fair bit of certain accuracy metrics. It could be R square, it could be a mean absolute error, root mean squared error, depending on your case, or what do you want to penalize. That is one thing. And secondly, when it comes to a complex system or non-ideal solutions, you try to validate that with some simulation. So you do a model, you try to predict the output, you try to predict the same output with a rigorous simulation, or using some rigorous property packages, let's say in Aspen Plus, and then you try to validate that. But again, having said this, if there is any upstream large fluctuation in the feed stream, maybe composition, mostly it happens in decision column, your model will not be of capability to predict the composition in a good accuracy. So what do we do for that is, again, I'll be discussing in the next session in detail, but I'll just to answer your question. What do we do for that is we try to we basically try to do data imputation, or developing synthetic data. So let us say that my feed has varied from 80% methanol, 20% water to 70% ethanol, 30% water. This is only data that I have. What if my feed composition drops down to 50%? Will my distillation column be capable to handle this kind of upstream fluctuation? Or in that case, what will be my upstream composition? So for that, along with the historical data, you also add a synthetic data generated by simulation to this. So your model becomes robust, it becomes capable of predicting values of situations that it has not seen in the historical data. So this is where the hybrid modeling comes up. I'll be touching to that shortly. Hybrid modeling approach, where your domain knowledge kicks in along with the historical data. Does that answer your question, sir?
Thanks, sir. Yeah, thank you.
Okay. So in the interest of time, I'll move ahead to the next area of application, that is development of surrogate and proxy model. Now, sir, I'm just taking the same example and going ahead. What if there is a new situation that we had a model working quite fine? What if there is a new situation that has arisen, and now the model tells you, or the model, or you want the model to predict for this fluctuation also? So at that point, you cannot go back to Aspen, or you cannot generate a synthetic data very quickly. So what you do is, for a real-time optimization or for a quicker solution, you develop a low fidelity surrogate or a proxy model that is just as good as your Aspen model, but it does not take a huge time as your Aspen model. So what you have already done is, so I'll come to the optimization along with this. So what is a conventional optimization strategy is, you have your first principle models. Let us say I've developed a model in Aspen Plus, and what you can do is you try to optimize that, have a stop criteria, and you get optimized parameters. So you can simply link Python or genetic algorithm or genetic optimizers in Python and try to link it with the Aspen and try to run this loop, get a set of good optimized parameters. However, in real time, if you want to do this, what you do is you generate a master data set. You do a perturbation to your first principle based model. Maybe it is CFD or simple sequential modular solver like Aspen Plus simulator like DWSim, for example. So you take extensive guesses. What could the temperature variations be? What could the pressures or parameters vary? You try to generate a data set. Then you run some ML algorithms. You develop a similar model with a similar accuracy, and then you use that model for control relevant modeling or in real-time optimization, where let's say if Aspen model takes 3-4 minutes to solve, the ML based proxy model will just take 3 to 4 seconds to solve. You develop a surrogate model. So instead of predicting y equal to f of x, you try to estimate that y with y dash equal to f dash of x. and then you use the optimizer setup. So this is a simple use case that I had developed, wherein you develop a control relevant model which could be used in predictive analytics. So I'll touch to this in detail, but maybe I'll go ahead. So typical workflow for a prescriptive analysis or a soft sensor is you start with the input features. So again, this is very important. Domain-based feature selection is likely to have a very good bit of accuracy, because you know what could impact what. So if someone is telling me that, okay, there is a purity problem, and I am changing some parameter which is not which is not impacting my purity, there is no point in doing that, right? So of course there are some data based techniques to find the correlation, like what could be the set of parameters that is impacting your target parameter. But if you have a hunch of your experience or a domain based analysis, this process becomes quite easier. So I know that if I'm working on a distillation column purity prediction, I will not go far upstream, or I'll not go downstream for sure. So this understanding is important, because if you just rely on pure data, you'll have tens and thousands of parameters that you will vary, and then you'll check, okay, which is the best, which is correlating with my target variable. So that is where again domain is important. You might need some data transformation, some filtering, and lag averaging. So lag averaging is basically again very crucial, because all our process engineering applications, all our chemical plants are systems with huge delays. Something that has happened but 2 hours ago in the reactor might impact my distillation column right now. So when I'm trying to map the product purity, what has happened in the reactor 2 hours ago is to be considered, rather than what is happening in the reactor at this point of time. So you know these systems are having a huge lag, because these are having high capacitance. There is a lot of material stored in between the reactor till my distillation column. That is why averaging the lag is extremely crucial, and this could be done purely on domain knowledge. Albeit there are some techniques in data, but again, if it is coming through domain, nothing nothing better than that. Then comes your prediction of KPI. Then you develop a model which will give you what will be your target parameter. Then you use the target parameter map. So basically you have a map which tells, if this is my x1, x2, x3, this is my y. Now you know this map, you try to find different x1, x2, x3 which will give you your target variable y in the required range. So that is the optimizer or prescription layer. And then you have to do some post processing. Again, domain knowledge comes into picture, because you will know, if the data tells you, okay, increase your steam wall to 100%, it might not be feasible in terms of safety or in terms of operations. So there you'll have to put your domain based constraints, and then recommend a set point. What should be your x1, x2, x3. So just try to, since we were already discussing soft sensors and advanced control strategies, AI driven optimization, this is a typical flow diagram in how we develop this predictive and prescriptive analytics in industry. Any questions on this? I hope this this helps in clarifying the earlier images also. So now coming, giving you some insights into what happens in the industry. This all looks good on paper, but what happens in the industry is, what could be different data sources, from where will my data be coming from. So in an industry, there are major 3 or 4 sources for data. One is the tags that comes through your DCS PLC, which is stored in a historian. The temperature, pressure, flow rate profiles, etc. is all stored in the historian, and you can get the real-time or historical data for all these tags through this line, through this pipeline of historian. Next, what you need is also the laboratory data. laboratory data like purity, concentration, viscosity, XYZ parameters. It could be some mechanical index or some physical parameter for particle size distribution, for example, if it's a solid operation. Next, important for predictive maintenance is the maintenance data. How many times the repair works was done, what was the root cause for that. Everything is stored in your ERP, SAP. So the equipment failures, repairs, maintenance done, all data is also what you need. Then comes your again a crucial is your information given by the vendor or the technology licenser. They will tell you what should be the ideal temperature profile. They'll tell you what should be the ideal pressure distribution in a distillation column, or if it's a reactor, then how should be the temperature across your catalyst bed. All these things will be given to you by the technology licenser. Now, this is important for extracting insights from sensor data to actual actionable items. But a major challenge in chemical industry is the different frequency that this data comes in, and how do you correlate it with each other. So for example, let us say that my temperature pressure flow rate comes every minute. I have every minute data available for my temperature, pressure and flow rate, or everything that comes through my historian. However, when it comes to lab data may not be available for every minute. You might have only one value or only one reading in one shift for a particular key performance indicator. When it comes to maintenance and work, you might have one value in 1 month maybe. And when you come to vendor supplied information, you might have only once in your entire lifetime of the plant. So the point I'm trying to highlight is that the data flow in chemical industry is highly multivariate, and it has a varied frequency. Data from every bucket is at different frequency. It is the data analyst's or data scientist's job to correlate this data. First thing is to synchronize this data. If you are not able to map the data correctly, the however advanced model you use, it is not going to help you. The most crucial thing that needs to be done is the proper synchronization of data. So I explained the lag averaging example earlier. That is very important, because you need to know what are the time frames that will impact my target or predict the variable that I want to predict. So synchronizing this data is highly challenging, and again the data is quite sparse. So laboratory data is available only once a shift. So when you try to develop a model, what you will have is, let us say I have x1, x2, x3. These parameters I have at every minute, but for these x parameters, I don't have the corresponding y parameter. Y parameter I have only once a shift. So what do you do in this case? Particularly in batch processes, you have data only at the beginning and at the end. But the leadership sitting at top of you will expect you to predict the temperature, pressure profile in the entire time of your batch, 20 hours, 30 hours, 40 hours. So in that case, what do you do? The labels are quite sparse. You don't have data. So one of the techniques that I mentioned earlier is you generate the data. You use your domain knowledge, you use your domain tools to ingest the data synthetically. So it is not a historical data, but the data you need to bring or generate it in a synthetic way. Then there are lots of mathematical or statistical techniques that will help you correlate this data, even though it is sparse. You might take some medians, you might do some data transformations, etc. I'll not go into the mathematics of that, but there are lots of techniques available that you can check. But the underlying point I'm trying to highlight is that synchronizing data available at different frequencies and bringing it onto a same level is a challenging thing. Again, then there are issues like missing values. Sometimes your temperature thermocouple is not in the mood to give you a good data. It throws 50 degrees Celsius in a furnace of 1000 degrees Celsius. What do? You can't rely on that. You can't say, okay, this is correct. So there are some certain mistake proofing techniques wherein you have multiple thermocouples and you take average. So even if one fails, others you can rely on. So these are just certain things I'm mentioning. But the idea here is that the data might not be complete there could be some missing values. You might need to think of data imputation. You might use some mean values for that time period. You might use some moving average kind of a strategy for compensating for this missing values. The sensors drift over a period of time, so it is important for you to calibrate the sensors, but if it is not done, you need to highlight or flag as a scientist that okay, the sensor looks to be drifting, we cannot use this data, we need to retrain the model. So it is not just you develop a model and deploy and your work is done. No, you need to retrain the model as and when the sensors drift, as and when there is a concept drift in the data. Just give me a second, I just need to do some technical arrangements. Am I audible now?
Yes, you are audible.
Okay, thank you, sir. So the non-stationarity kind of stuffs are also important because the data doesn't remain constant. It keeps on changing. So a model developed today might not be deployable tomorrow. So it is important for a data scientist to compensate for these kind of data drifts. Some manual interventions, wherever there are manual interventions, the risk increases. So I'll tell you a funny incident when we tried to work for industry that I'll not name. But when we looked at the data, we tried lots of advanced. It was my initial project or my initial assignment in my first consultancy assignment during my PhD. So we were trying to look at different data correlation and nothing was coming up. So when we tried to look at the operations, and then I understand, and this is across entire industries, many a times the operators might not take the samples on time. So if it is a time sensitive process, the operator is instructed to take a sample at 12 p.m. He might, he might be busy in some other operation, or he might not take it seriously and take the sample at 12:30. But that 30 minutes time becomes crucial when you are asking the data scientist to predict this parameter for next 30 minutes or next 1 hour. So these things which you cannot control, but these things are need to be considered when you sit for making these kind of predictive analytics models. So it's a funny incident, but what we understood is you might not completely rely on data that has manual interventions. So you need to compensate for that. So you might need to take some correction factor and try to recalibrate your models and so on. So these are just issues that I just wanted to give you a feel of. When we work in academia, the models work very good, but when it comes to industry, what could be the challenges and how it needs to be thought on. I'll discuss some best practices and some challenges or some troubleshooting techniques in the second session of typical case studies. But I hope this gives you a gist of what could be the problems occurred and from where the data could come. It is not just PLC, it is not just SCADA or just DCS is giving you data. No, you have different sources from where the information comes, and it is our duty to utilize this information in a constructive manner. So any questions on this? Any thoughts, any comments? All right, let's move ahead then. So coming to the different modeling approaches. So although predictive data analytics is mainly data driven, as the name itself has, there are techniques like white box modeling wherein you use the first principle based model to predict your KPIs. I've just listed out some differences between first principles and data driven black box. So initially I referred to the data interpretability. So when I talked about the interpretability of the data model, what I meant was sometimes you have a model wherein you are feeding some value, it is giving some output. but you are not able to interpret that output. Why the KPI is increased, why the KPI is reduced, because you don't get any insight into the equations. These equations are all simple mapping, or it could be some gradient or tree boosting or tree based algorithms or models. So you might not be able to correlate physically. Whereas if I look at the let me take you back to the earlier two equations of reactor temperature estimation. When I look at the first model, I can easily tell, okay, my flow has increased. That might have caused an increase in my temperature. Or let us say that there is some issue with the jacket temperature that is causing my reaction temperature to change, or my feed has changed, my density has changed. That is why there is some change. But when you look at the second equation, you do not know what is the parameter impacting. So you don't have any way to validate whether whatever you're getting is correct or not, unless you do a proper validation as per the methodology. So that is why it is very crucial to look into the black box model. And when black box model does not tell you any insight. So by the way, what are these black box models? So these are tree based models. So for example, a simple if else loop or a simple classification problem. If you tell that historically, if my temperature is above 500 degree, there is a problem in the reactor. So it is just imagine a tree where it says that okay, t equal to 501. If it is greater than 500, there is a problem. If it is less than 500, it is okay. So you do not know whether the problem is real, what has caused the problem. You know nothing. It is just a tree based model. So there are several linear and semi-linear techniques. Like there are lots of linear regressions. There are principal component analysis based models. Then there are nonlinear neural networks, deep learning that has come up, tree based models, etc. I don't want to go into the mathematics because it will be a separate session altogether. But just to mention that these models might not always give you insights or always help you in terms of interpretability. I'll discuss one technique wherein a tree-based model, you can use a certain operators to extract some interpretability or extract some physical significance of how the model is working, or how the features that you are using to the model are contributing to your output prediction. So instead of just using your data or just using your knowledge, you try to combine both of them, and that is where the hybrid modeling comes into the picture. So yesterday also Professor Goody mentioned a lot about hybrid modeling, physics informed neural networks and all. So what I'm trying to do today is just give you an idea what are hybrid models. And when I started reading into this domain, I always came across a typical question: how can you combine data and physics? How can you combine my data insights into my domain knowledge or physics based insights, right? Because when we just hear, okay, you use both of them, but how to use them, how to combine both of them? So there are a lot of techniques or a lot of approaches that has been reported and has been implemented widely, but I'll just touch upon a few techniques that will help you actually see how these two things could be combined. And also, I'll encourage the undergrads also, if there are participants or even the faculties, I'll encourage to float some course projects, some short projects wherein you can use some basic programming, you can use some synthetic data and try to combine data and physics. So the emerging chemical engineers already have that flavor of using hybrid modeling, because we have been traditionally using first principle based models. We hit a limitation in terms of computational resources. Then we moved on to a data driven model. We again hit a limitation in terms of accuracy, in terms of interpretability. So this is the era wherein you must be able to combine the data and the science behind that data. So
as I've highlighted here, the scientific knowledge may be insufficient for some complex processes. For example, if there is any fouling issue and you are using ideal assumptions, so even if it is a first principle based model, it might not give you a real case result. And your first principle might not be capable to incorporate all the actual world scenarios. Fouling is there, some issues with the flow pattern, some issues with the distribution, some issues in the equipment constructions. These might not be able to be combined. So that is why it is essential to combine data and science. That is where the hybrid modeling comes into the picture, wherein it combines the strength of the first principles mechanistic models along with the data driven insights, and it creates a quite robust systems. So with this notion, I'll just give an example. We all have definitely used Nusselt number equations or a lot of empirical correlations in our academia. So this is nothing but a good example of combining data and physics, wherein you perform some experiments, or even for that case, a very basic Arrhenius equation, which comes up with some kind of first principle modeling. There is some energy balance done, and then you use some parameters that have come from experiments, that is coming from data. So you correct your mechanistic models. So let us say you have your dy by dx equal to g of x and u, but this x g as a function of x and u could not give you good insights. So what you do is you perform experiments with x, u, and y. You do a regression, you try to find some parameter theta and try to embed that to your model. And this is the way you can rectify, correct, or augment your physics based model by the data correction factors. So this adds interpretability and to your black box models as well, and it makes the model more generalized, more robust. So any questions on the concept of hybrid modeling? Sorry, I'm having a bad throat, so I'm pausing in between to take a sip of water. All right. So when it comes to combining, again the same questions. Okay, I understood one approach. What about the other ways? How can we combine data and science? So broadly, on the upper at the upper level, there are two categories or two ways where you can develop this hybrid model. One is where the ML complements science, and the other is science complements ML. So when I talk about the ML complements science, the models are mainly science based, and there is just a flavor or a lesser part of data that has come to that. Like I mentioned that, let us say you are able to predict, you want to develop the heat exchanger outlet temperature. You want to predict that. You do a simple energy balance, and you find that whatever your theoretical value is there, you are not able to match it up with your experimental or the actual plant data. So what you try to do is you use the same mechanistic model, but you apply a correction factor that has derived from the data. So your mechanistic model is much closer to the actual world scenario, because there are some heat exchanger. When I talk about the heat exchanger, there could be some flow patterns that is not exactly accurate. You might have taken, if it is a multi-pass heat exchanger, especially, you might have taken a idealistic situation to do a modeling, which is not really happening. You might have cross flows in between. You might have fouling. You might have some baffling issues, etc. Some flow patterns which is not as per expected or not as per the ideal assumptions. So to compensate for all this, you take the experimental data, you do some regression, you find some parameter, and you then correct your science-based model using that. So this is one way. So we'll systematically look at different ways that you can do. I'm pretty sure most of you sitting here would have certainly used at least one or more of these techniques, but today we'll look at it systematically, exactly what kind of approach we have developed or we can use to combine data and the physics. So first way is in ML complement science, you can have a direct hybrid model wherein you can have first you use science and then you use ML. So that is a series approach, or you can have both parallelly and then you combine them. Or third way is to have a reduced order model. And second bucket, that is science complements ML, wherein you by and large have a data-based models, but you needed interpretability, you needed some correction, you needed some improvement on that data-based models. That is why you're incorporating a part of physics to your data-based models, maybe by design or by learning or by giving some constraints to the model. And then that is how you improve your data-driven model. So these are the buckets wherein you can have the science complementing ML models. So let me give you an example of a direct hybrid a direct hybrid and a series approach to combine data and science. So let us say I have a science-based model, and there are again two approaches. You can use science first and then data, or you can have data first and then science. So if I go from left to right, I'm using science-based model first. I have my operating and boundary conditions. I know all the parameters. I'm developing my model, which is giving me data. I'm using data augmentation and then training my ML model based on this data. So I know that my ML model will not violate constraints because the data itself is generated using all these constraints because I'm using a science-based model. That is why I can trust this model rather than just using a database model. I can have this data, I can have some additional data, train a model, and then I can get a output for predicting my quality parameter, for example. Second way is I have a plant process data. I develop a ML model based on that. I do a parameter estimation on that. I try to estimate some parameters, use that parameter then to correct my science-based model, as I mentioned earlier, and then I can do a prediction of my quality parameter. So in either of these approaches, you are combining data and science in a series. That is why this is known as the series approach for direct hybrid modeling. So this is usually used to add more features. For example, let's say that you are able to get temperature, pressure, etc. from your sensor data, but you do not have you do not have any composition feature. So you use your science-based model, you do some modeling or do some CFD over there, predict some composition, predict some parameters that you don't have, and then you develop again a AI model to predict the parameters. So it could be either used for soft sensors, like I mentioned, or it could be used for parameter estimation, or it is widely used to add more features that usually doesn't come from the data. So this is the series approach. Second is the parallel approach. So what you do in parallel approach is you run white box, you run black box parallelly, and you find out the residuals of both, and then you combine to get a final solution. So, for example, you have dynamic data, you have the boundary conditions, because largely your physics-based model will run on the boundary conditions. So you run your science-based model, you run your ML model, you get both these things. Based on your domain experience, you can adjust the weights of both of these, and then you can come up with a final output that will be significantly better than both of these individual outputs. So this is again one way that you can implement to improve your data results or improve your science-based results. The third way that I mentioned earlier also, while talking about the advanced optimization, is the reduced order models. Not every time you would be able to run a complex science-based model, particularly when you are into the realm of real-time optimization. And that is where a reduced order data-driven model becomes crucial. So what you do in there is you develop your science-based model, you develop a simulated synthetic data, and then you train your model based on that. So now this ML model will be almost as good as or as accurate as your science-based model. But the turnaround time or the solution prediction time of your science-based model is much higher than your ML model. So your ML model can quickly give you what would be your KPI. You can feed that to your optimizer. So the case that I discussed of the advanced optimization, you need that ML-based model to quickly give you the results, which is quite accurate, to quickly give you the map of X1, X2, X3 with your Y, and then based on that map you invert and then you find what is the best x1 x2 x3 for my required y. So this is the computationally efficient reduced order low fidelity model that is widely used. Coming to the area where the science complements ML, this is basically using your scientific knowledge to develop the ML model to make them more generalized. So, for example, when you try to select the model architecture, you try to select it based on some scientific insights. Like when you are doing some neural networking, or some kind of advanced algorithm, you need to tweak some layers, you need to tweak some parameters. So if you have a understanding of the process or understanding of the physics, it becomes easier for you to implement, or it becomes easier for you to tune your data driven models. It is not directly using the data or directly using the science behind the behind the problem, but to take insights from that. That is why the name is direct is used for where ML is complementing science, but here you use science complements ML. So you do some refining based on your understanding. So let us say, as I mentioned, when it comes to constraining your optimization or your prediction problem, it is based on domain only. Because when I say that my limit for my steam control wall could be from 10% to 60, 70%. So this 10, 60, 70 comes from my domain. So you are not directly using the science information, but you are using it indirectly to impose constraints on your data-driven model. So it becomes more refined. Many a times you need to do some refinement or some post processing of your a set point recommendation, because the maths can give you any value which is mathematically feasible, but it might not be feasible in terms of science or in terms of physics of the problem or in terms of the real time actionable items. So you need to do some post processing over there. You need to do some post transformation. So all these require the knowledge of domain, and the physics only will help you to take actions and make your model more implementable. It might not improve your accuracy. Generally accuracy is improved when you use a direct approach, but these kind of post processing or these kind of models where science is complementing machine learning will help you make your model more deployable, more implementable in the real time scenario. So this is I come to the end. I'll give you more. I mean, I'm trying to give you 30 minutes back of your time, because I'll reserve some of the parts for discussion in the next session, where it will be more focused on the case studies. So whatever concepts we have brushed up in this session, I'll try to link that with the real-time implementation. I'll try to give more feel of real-time data, more graphs, whatever I can. But just to end the session, I'll just highlight that, for a successful AI ML projects in chemical industry, domain knowledge is really essential, because that is what is the driver. That is where the problem is coming from. So to solve the problem, simply data is not sufficient. When it comes to predictive analytics, it is important for you. So this is the takeaway that I'll try to give you, that understanding data analytics, statistical techniques is extremely important, but having a background, having a hunch over your domain is extremely crucial, because that will help you deliver physically meaningful models. So because the operator Imagine you're an operator, you're working since 30 years and you go and tell the operator, okay, this is my model. I've done some advanced mathematics, some advanced predictive analytics. You deploy there, whatever it tells you, you take action. He'll definitely have a resistance because he'll first look at the interpretation of what the model is doing, right? That is why I am again and again emphasizing, sorry if it is too much repetitive, but this is what I have learned in the industry after graduating from a academy and transitioning into industry. It is important to know that domain is very, very essential along with the data-based techniques also, because it becomes more physically meaningful. You are able to respect all the constraints of mass or energy conservation, stoichiometric constraints, the reaction constraint, the kinetics is what you know. So that makes the model more deployable. The interpretation of anomalies versus transients, safe deployment, as I mentioned earlier, the understanding of synchronization between the data, different frequency data, mapping it together on a same level is again important. Choosing the correct operating regime, validating the model, as sir asked a very important question that even industrialists are struggling today. Model validation beyond statistical metrics, because the plant operator is not happy with showing R square of 0.8, 0.9. The plant operator needs how it will help me in terms of physics. So all this combining your data driven insights along with your domain knowledge is something that will really help our chemical industry not just thrive but to sustain, make it more environmentally efficient, make it more operationally efficient, and overall have a good sustainable future. It is essential to have a predictive analytics, not just predictive, uh, a prescriptive analytics, holistic approach which encompasses data, which encompasses your domain knowledge, will help us have a better ecosystem wherein AI ML can actually thrive in the chemical industry. With this note, I'll just end by saying that certainly it is important to take a good hand, to have a good hand on data science, on data analysis techniques, along with a along with a domain expertise. So I'll end my session and give some time back to you for lunch. Please ask any questions. Thank you. It might not be just question. It could be some thoughts, some comments, some suggestions. Everything is welcome. So it becomes more interactive, right? It is not a lecture. It is a FDP.
Sir, students have posted their questions in the Q&A.
Okay, that's great. Do I have access to the Q&A, or can someone please read the questions for me?
Sir, I will read the questions, sir.
Okay, please, yeah. Thank you.
Can this strategic prescriptive analysis model, which help optimize operations, be explicitly tuned to minimize atmospheric emissions while still maintaining production targets? For example, can system prescribe a specific temperature or flow rate that reduces off-gas flaring?
Yes, certainly, yes. There are lots of industrial projects going on this because minimizing flaring is again a very crucial area. Not just flaring, wherever there are losses into the atmosphere, you could be venting some excess steam to the atmosphere. You could be doing any sort of material dumping into the atmosphere, which is not good from environment also and from cost also, because you're making some gases and you're just flaring it off is not good for the environment or not good for the economics or monetary health of your plant also. So definitely a plant-wide approach. So this is where AI helps, because you cannot develop science-based model for every small equipment, because when it comes to flaring, there are different units in the entire plants that is impacting your flaring, or let's say venting of gases. So a plant-wider approach wherein data is used can definitely be used to give a prescription for different sections or different areas of your plant, so as to minimize a common goal. So to answer in short, yes, prescriptive analysis is being done on these kind of applications.
Sir, I had a doubt regarding the implementation of this predictive analysis in the industry or a plant. Will it be a type of a work or a part of a R&D department, or we can hire an external agency for executing it in a plant, or to make a whole design for it?
So it depends on what are your capabilities, because trust me, in today's era, you come up with a problem and you have a solution already available in the market. So are you ready with the capabilities? Are you capable to implement it on your own? Well and good, go ahead. If not, you'll have a third-party consultancy agencies which will help you drive this solutions and implement on your site. So because this requires, because as I mentioned earlier, not all industries have, especially small industries, might not have a R&D or might not have a digitalization team. So in that case, they approach a third parties, or even the bigger industries approach third parties, because the third party has a expertise. The consultancies have an expertise on driving such kind of industry 4.0 projects. And it is not just R&D department. It is mostly the operations. It is also the maintenance, R&D, and it is central technical services that usually comes with this, or process efficiency improvement. There are different departments in industries driving this kind of enhancement or improvement project. So this project is a larger project. It is not a small project. It has to be a cross departmental efforts to drive industry 4.0 projects. I hope that answers your question.
Okay,
Yes,
any
sir.
other
Thanks
questions?
for-
Any other questions?
Dr. Nimish, I've got one question.
Yeah.
Actually, your suggestion, you've got a very rich experience, and you mentioned that for undergraduates, some artificial development programs can be undertaken. So, based on your experience, what are those areas? Say heat exchanger, installation column, or oil and gas separator. What you see that such courses for undergraduates that can help?
Right, right. So I usually feel that the once the statistical techniques are clear to the UGs in their maybe second year or so, or third year for perhaps, whatever chemical engineering courses they are working on. So let us say it's a thermodynamics course. You can have a short data generation and model development activity. So for example, I'm working on a flash vessel, and I need to estimate the amount of, as you mentioned, oil gas separator, or any flash vessel wherein there is some liquid coming out from bottom and there is some gas going up upwards. So in industry also, you might not always have a composition analyzer, that how much water is being condensed or how much gas is being coming out from the flash vessel. So this is purely thermodynamics, right? So when we are taking these courses of thermodynamics and teaching this flashing or Gibbs potential, uh, activity could be done for the students to run the simulations on a simulator, generate data for a range of temperature, pressure, composition. Different groups could use different models, like someone could use a tree-based model, someone could use a linear model, someone could use a neural network. And using the same data, you can generate different models, have a comparison between them. So the students also get a feel of developing a proxy model. The model that will perform better could be then used could be used real time in the industry to predict the amount of gases going at top and amount of liquid coming at the bottom. So I just give an example of thermodynamics. When it comes to distillation also, you can have a typical distillation column, a simple one, wherein you choose what could be your control handles, reflux ratio, reboiler ratio, some temperature or so. So at UGs, what I suggest is you might not have a industrial data, which is fair enough. So why don't we start with a reduced order model, which is in our purview or which is in our scope. So we can use simulators which are readily available. There are some free source simulators also. You can use that, generate the data. So at least at that level, the students will get acquainted to or will get familiar with how the ML models could generate insights or could predict our chemical industry KPIs. So it could be used in widely operations. What I suggest in terms of actionable items is whatever blocks are available in your simulators, may it be flash vessel, it could be heat exchanger, it could be a distillation column, it could be a compressor. These four are very popular area which are also required in industry. So that will give a leverage when the student goes into industry, particularly in such consultancies which use or which use data driven analytics. It becomes easier for him to handle with the data or at least quickly generate some insight, because he has already seen a or he has already worked on synthetic data. It becomes easier to transition onto real time data. So that is what I would suggest.
Yeah, thanks.
Any other questions?
So very important suggestion. Thanks.
Thank you. Thank you.
Any other questions? Okay, so I think so I would like to extend my sincere thanks to Dr. Nimish sir for giving this excellent lecture on predictive analytics in the chemical industry operations. I think the final year student must have understood what sir was talking about. They have studied process control, but those are the second year, third year student, they may not understand now. Anyway, this was a good lecture, and I also offer my thanks to participants and our faculty members. Okay, so the next session we start at 2:30. So madam, should we end the meeting now?
Yeah, we can, and let the participant join again at 2:30.
The
Nimish, it
meeting
was such an insightful session. We're looking forward for your next session in the evening.
Sure, ma'am. I think it will be more clearer, because when I show you the data, you'll get a feel, or the participants will get an idea, okay, how the temperature is rising, how it is lowering, how the analytics helped us. So I'll just try to touch upon that in whatever is in my capacity to avoid confidentiality issues. Thank you.
Okay, madam. So I will end the meeting.
Yes, yes.